The sun's energy. If you were to ask the next 5 people you meet, what is the most important object in the sky, most people would say our sun. The reasons for the sun's importance are many, including that it provides light to warm Earth's surface, it provides the energy that drives weather, and it underlies the ability of plants to grow through photosynthesis. Our sun also plays an important role in the cosmos. The sun is the largest member of our solar system. It has almost 1,000 times more mass than all the solar system's planets, moons, asteroids, comets, and meteoroids put together. But the sun is also a star. In fact, it is a remarkably typical star with a mass, size, surface temperature, and chemical composition that are roughly midway between the extremes exhibited by the myriad of other stars in the heavens. For most people, what matters most about the sun's energy is the energy that it radiates into space. Without the sun's warming rays, our atmosphere and oceans would freeze into an icy layer coating a desperately cold planet, and life on Earth would be impossible. To understand why we are here, we must understand the nature of the sun. Why is the sun such an important source of energy? One reason is that the sun has a far higher surface temperature than any of the planets or moons. The sun's spectrum is close to that of an idealized black body with a temperature of 5,800 K, see figure 2 to 12. Thanks to this high temperature, each square meter of the sun's surface emits a tremendous amount of radiation, principally at visible wavelengths. Indeed, the sun is the only object in the solar system that emits substantial amounts of visible light. The light that we see from the moon and planets is actually sunlight that struck those worlds and was reflected toward Earth. The sun's size also helps us explain its tremendous sun's energy output. Because the sun is so large, the total number of square meters of radiating surface, that is, its surface area, is immense. Hence, the total amount of energy emitted by the sun each second, called its luminosity, is very large indeed, about 3.91026 watts or 3.91026 joules of sun's energy emitted every second. Astronomers denote the sun's luminosity by the symbol L. A circle with a dot in the center is the astronomical symbol for the sun and was also used by ancient astrologers. What makes the sun shine so brightly? Albert Einstein discovered the underlying key to the sun's energy source in 1905. According to his special theory of relativity, a quantity m of mass can in principle be converted into an amount of energy E according to a now famous equation, Einstein's mass-energy equation E equals mc2 amount of energy into which the mass can be converted. In joules m quantity of mass, in kilograms c speed of light 108 m/s the speed of light c is a large number, so c2 is huge. Therefore, a small amount of matter can release an awesome amount of energy. Einstein didn't fully appreciate at the time how tremendously his ideas would impact astronomy. It turns out that the temperatures and pressures deep within the core of the sun are so intense that hydrogen nuclei can combine to produce helium nuclei in a nuclear reaction that transforms a tiny amount of mass into a large amount of energy. This process of converting hydrogen into helium in the sun is called thermonuclear fusion. It is also sometimes called thermonuclear burning, even though nothing is actually burned in the conventional sense. Ordinary burning involves chemical reactions that rearrange the outer electrons of atoms but have no effect on the atom's nuclei. Thermonuclear fusion can take place only at extremely high temperatures. The reason is that all atomic nuclei have a positive electric charge and so tend to repel one another. But in the extreme heat and pressure at the sun's center, positively charged hydrogen nuclei are moving so fast that they can overcome their electric repulsion and actually touch one another and combine. On Earth, the same thermonuclear fusion provides the devastating energy released in a hydrogen bomb. You can think of protons as tiny electrically charged spheres that are coated with very powerful glue. If the spheres are not touching, the repulsion between their charges pushes them apart. But if the spheres are forced into contact, the strength of the glue fuses them together. Without its single electron, the nucleus of a hydrogen atom, H, is the same thing as a single proton. In much the same way, a helium atom, E nuclei, in the absence of its two electrons, consists of 2 protons and 2 neutrons. When they combine with a concurrent release of energy, we can write the nuclear reaction as for He and energy. For every 4 hydrogen nuclei converted into a helium nucleus, for 0.31012 joules of the Sun's energy is released. This may seem like only a tiny amount of energy, but it is about 107 times larger than the amount of Sun's energy released in a typical chemical reaction, such as occurs in ordinary burning. To produce the Sun's luminosity of 3.91026 joules per second, 1011 kilograms, 600 million metric tons of hydrogen must be converted into helium each second. This rate is prodigious, but there is literally an astronomical amount of hydrogen in the Sun. In particular, the Sun's core contains enough hydrogen to have been giving off energy at the present rate for as long as the Solar System has existed, about 4.56 billion years, and to continue doing so for more than 6 billion years into the future.